everyone, we're gonna start now. Welcome back from our summer break to our new season of AI/ML Conversations. Hey! I hope everyone had a great summer, or at least has something they've done this summer, one weekend or something, I don't know. Anyway, I see a lot of happy faces that everyone kind of wants to maybe jump back to AI/ML. So, welcome on AI/ML Conversations. What's AI/ML Conversations? I'm gonna do a quick intro for someone who here the first time. It is yet another AI/ML conversation. No. Basically, it started as a just group of people. We was meeting out in a bar over here, chatting about like ML, and then at some point there was like a brilliant idea: why not to bring this good vibe and good experience to some bigger place? And fast forward a couple of months, we are here, and we created this meetup mostly to give a spot for people who want to share their experience working in AI/ML space with their community, and and we want to make it sort of like in between from sort of like official event and also just friendly chat. And we hope that our meetup is sort of the middle spot where people at the same time can just casually chat as well as sharing some really good work that they have done in their career. So we welcome people from all their scale, from AI/ML, from entrepreneurs to researchers, from students, everyone who wants to share something. And we are growing. We started as just 4 people in a coffee house, me and 3 other guys who was promoting their own event at that time. So now we have almost like 400 people. That's awesome. And introducing ourselves, I think I should start with that. My name is Vlad, and the rest of our team is Anne and Hyun somewhere here, and Anna, saying hi from Boston this time. If you have any questions, any ideas, suggestions, we are here. Feel free to ask us anything. Text us on LinkedIn or whatever. We have a code of conduct. So it's borrowed from Angular NYC. Basically, just be respectful to each other, and we take this serious. If you feel something is off and something is inappropriate, please reach out to either of us, and we will make sure that it won't happen. And we have a Discord chat. Please join us. It's not that active yet, but we want to make it sort of like a meeting spot where we can collaborate and brainstorming about like how we can grow this event from just meeting over for official meetups to kind of something more like fusion, more kind of self-organized, organized stuff. So feel free to join. If you need this link, ask me after the event. And super moments. For one of you who are here from the super moments, here's our QR code. If you missed that, I will put it on the site after the event. You'll have a chance to check in. So, housekeeping stuff. We have our 2 restroom, like main restroom on the left, and women's restroom, I believe, all the way down. All the way down. All right. Yeah. And after this event, so like the program is we'll have 2 speakers every time. Our event, we have 2 speakers who give some awesome talk about the experience. We have a quick break in between. So the first the second speaker gonna start at 7 p.m. and then the official part will end at 8:30-ish, and after that we're gonna meet in the Old Town Bar. So for a drink or something, just feel free to join Tuesday night. It's a great time of the week to get some extra beer that you're gonna regret in the next morning. Anyway, and so in actually one of the most important part. This event cannot happen without our speakers, and we were actually very surprised that because we were thinking, okay, like it's gonna be very hard to find speakers. Nobody will gonna want to talk in front of random people at some random meetup, but it turns out that a lot of people want to share their experience, and that's one of the purpose of all this enterprise. So we encourage people to come on stage and share their experience. Okay, QR code this morning. Let me. Anyway, so I have a QR code that is a form for submitting for a speaker. You can ask, you can ask me or our organizers about how to become a speaker. We welcome everyone. So the second thing that our meetup cannot be possible with is our amazing sponsor and supporter, Capital One. And with that being said, I'll pass the word to my happen to be Capital One employee, co-organizers of this event. Good.
The applause should be for Capital One for sponsoring the really great pizza, for having us in this building, for Kramer there, who is setting up the audio and always doing a really great job, and for all the support staff, the front desk, the downstairs desk, and the people who set up this chairs and everything. So thank you so much for organizing this and for making this event a great place where people really like to come. So yeah, please give it up for Capital One. Yay! So, Capital One is hiring as well, so that's one of the reasons that why they agreed to sponsor this. Capital One is big in the AI ML space. We have a really big team, and we are all about changing banking for good, which also involves adding more AI, more ML to banking to make people's lives easier and happier when they use banking. So, how does it work to apply for Capital One to have a job at Capital One? Well, you can talk to either of us. Or to make it easier, Ian has devised a very great system called a QR code, which you have seen, so which he can talk a bit more about.
Hello. Yeah, that's the gist. There's no shortage of QR codes at this meetup. So these signs you'll see both like near the food and on the edges over there are going to have a link that will give you all the instructions that you need to know if you're looking to get referred to get a job here at Capital One. Because you've shown up, it already gets you a leg up in the whole application process. So if you have any questions, just let us know. We'll be happy to help.
All right, so with that said, thanks again. And I'll first, before we go to the speaker, Shafik, who's going to talk about multi-agent, I want to give a 1 minute quick presentation, quick time for Silva, who is one of our previous speakers. So if you've been to one of our previous speakers before the summer, you've probably recognize Silva. So he's going to talk about a fantastic thing that he created.
Thanks a lot. I want to present you a prompt competition bot. Here's the QR code. It's possible to compete on Telegram. The idea is quite simple. You'll be given a simple task, like a short snippet of text, and you ask to extract certain type of information. Maybe it's something to do more. More task will be lately, and you have to find the best prompt. So you have to find a prompt that would hit the most of the score. For example, you have text extraction. You get like simple intersectional reunion score. And the better score you have, on average, the better you are. So just try it. I hope you like it.
Thank you, and Seva is, as we mentioned, one of our first speakers in our meetup actually, and it was he gave a very good, great talk about Llama. Sorry. Oh yeah, right. right, for diffusion model, and I think we have it recorded actually in our, no? Oh, that was the first time when we lost our recording also, like a few times after. Anyway, so yeah, we have Telegram, check it out. And that being said, we're gonna pass our word to our first speaker, who so welcome is Shafik. He is a senior Android and ML engineer at New York Times, and she's gonna tell us about core theories and behind multi-modal AI models. Welcome.
So there seems to be some like additional sound coming from my computer right now, like some classical music. That wasn't intended, but I guess it's nice. So when I get to the video, I'll see if I can test it out and see if you can hear it or not. Hopefully you'll be able to hear it. So introduction to multimodal systems. I guess a quick show of hands at this point. How many people are familiar with multimodal AI? Okay, all right. Okay, cool. So how many people would say that they're familiar at the model level and at the deeper level a little bit and how that works? Okay, so that's essentially what my talk is going to be focused on at some level. So I will be going a little bit into those details as far as the machine learning is concerned, but not enough to inundate anybody too much. So the outline of the talk is now I confirm this assumption that a fair amount of people are familiar with multimodal AI at some level and multimodal models. I'm going to start off a little bit talking with multimodal perception and how people kind of perceive multimodal scenarios. Then we're going to talk about multimodal machine learning, which is kind of the crux of where the AI element comes in. And then I'm going to be talking about a few multimodal frameworks, demos, and applications. Some of this is this is actually original talk is a much longer talk, and I might split this into two separate parts for this kind of context. But as far as, I'm going to dive into a few different pieces here. And also for anybody who's a coder, who's into Colab, putting things together, putting models together and trying them out, I do have a few notebooks available where the demos are actually incepted from. So firstly, I'll just start off basically, what is a modality? So modality, according to the definition, very commonly found online, refers to a specific type of input data, such as text, images, audio, providing informational content integrated to enhance model performance. So that's a modality in context of machine learning, and in a modality in context of human perception is literally any form of unique input data with an energetic source. So the sound that you listen to is, for example, a modality, or the vision, the images that you see is a modality. It's interesting because there's, I'm not going to go too deep, but there are some dimensions as to what constitutes a modality, but for our purposes, we're going to get some basic level understanding. So a little bit of context and where I came in. So my research years ago started in the field of statistical signal processing and essentially multimodal applications to sensor fusion. 6 years ago, before the AI current revolution took over, for a lot of like social advancements in AI, 2010s came into fruition. Again, the little bit of context in my background with multimodality. I was working for the U.S. government where I was working on sensor fusion, which is essentially where you take several different types of sensors, which include sensors, seismic sensors, camera visual sensors, sensor, and ultrasonic sensors, another example. Essentially, you use those together for the purposes of intrusion detection. What that means is intrusion detection is like if somebody's enter a perimeter, you have several different types of sensors around the perimeter to be able to combine their intelligence in order to find what that could be. Before a lot of the modern techniques, and modern in the last few years have come out for like advanced image processing, there are a lot of probabilistic. This is prior to before deep learning started taking advantage of big data. We started to work with things like Bayesian belief networks or other kinds of machine learning models that were not like categorized as machine learning. You had things like self-organized maps. You had other types of algorithms that were more mainstream in the world of AIs, recognitions, etc. But in particular context, we were working with probabilistic called Shafik. I don't know how many people have heard of that before. Probably not too many, unless you're a um, Bayesian belief uh, statistician. So DST involved a combination of handcrafted belief functions that act as characteristics of a particular environment. So what belief functions were that they were people contributing their intelligence experts to the probability distribution of a particular phenomenon. And they were using mathematical techniques to do so in many cases, estimation and kernel density functions, other interesting things like that. And essentially, the EST belief system was combined into multi-sensor security systems. And this is just one of many techniques, but with the combination and the summation, essentially, of all these belief functions, appropriate summation, we're able to come up with a multimodal system in order to detect somebody coming into your environment. So this is more specific visual example. So we had the left what's called ultrasonic molecular Doppler signals, which is you can think of it as sonic radar. As you're walking, if you're familiar with radar, how the radar works, signal bounces back and forth between the radar receiver and a source that you're trying to target. Is similarly you can detect ultrasonic waves emanating from a source as the source is moving. That's where the Doppler effect comes into play, and you can detect appendages, other characteristics of somebody or a dog or a cat or a person moving. That's what the spectrogram on the left is showing. Then you can combine that with the motion of a person walking across the ground, and they are causing seismic disturbance on the ground that can be picked up with a seismic sensor where you're detecting X waves, etc. So essentially, those were just a visual example of those modalities. So now I'm going to just give you a video of a perception. Like set on a little bit of a back.
Watch this experiment. It's called the McGurk effect.
Ba, 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 ba.
What do you think he's saying? If you think he's saying da, 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 you are in the grand majority. But now, close your eyes and listen instead of watching.
Ba, 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 this person saying as
the voice is saying
close your eyes.
ba, ba, ba. Now, let's replay it without the sound.
Open your eyes and watch, what he's saying, but his voice is muted. Then it'll look like da, da, da. So essentially,
yes, it's true. His lips are saying ga, ga, ga. So how is it that when the lips are saying ga, 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 and the sound says ba, 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 that our brains read da, da, da? The McGurk effect. It's an example of an auditory illusion. It's a great way to show that the accurate perception of information can involve the participation of more than one sensory system. In this case, vision with sound. We call it multimodal.
Again, the quantitative description of the McGurk effect, right, is essentially when there's large discrepancy between what is heard and what is seen, the brain treats them as two separate events. So, for example, if you have two things that are far away, if you have a drum beating, the visual of a drum beating, and if you have a sound of a drum beating and they're separated in time, you'll see those as like two distinct, different events that cause that, right? If you see them close together, in the middle where the discrepancy between the two signals is small, so you can see these are different signals, sound signal and a visual signal. They look like the same event. For example, if you see that the drum occurs about at the same time vision of your visual of the drum hit the skin occurs, then you will have it'll look like the same event. Then when you have intermediate discrepancy, the brain actually is not sure that it is. And then it's doing essentially multimodal processing. If you do a best estimate of that, using a lot of values in the brain environment, not acceptable. So this is kind of, I just wanted to draw that analogy of what multimodal is. That is essentially true understanding of our environment requires this multiple modality. You can't just rely on mechanisms. You have to rely on that. I would like to get this going, by the way. So, just to give you an understanding of unimodality. There's specific architectures for handling unimodal. So, for text, the state-of-the-art models are transformers, capturing long-range dependencies. Okay. For images, you have CNNs, and then you also have vision transformers, which are the state-of-the-art models. Then for audio, we have actually several models for this purpose. But at one point, RNNs were current neural networks for the main ways people would use one of the models to understand audio information. Because audio information had time signature for really once they use the data. So and then on the right, you have a spectral band, which kind of is a little bit of a multimodal combination of this data streams. So you have CNNs, RNNs, and so you can get like audio perception. So before we go into like what multimodal understanding is, right? So essentially, you have the idea of cross-modal interactions. So essentially, multimodal. We're going to talk about multimodal embeddings, but when you have two sources of data, they interact. For example, if you have text data with sound data with image data, there's essentially a computational interaction between both of those in order to align those semantics. What semantic alignment means is that information from the two sources are correlated with each other. Cross-modal interactions, the understanding of them helps be able to take into account complementary information across different modalities. So image data that indicates something is happening may indicate only part of the picture, but sound data can indicate more what's going on in the entire scenario. So understanding and modeling these interactions allows for things like multimodal sentiment analysis, visual QA answering, and human-computer interaction systems, and audio image captioning. All of these systems, I imagine people are familiar with. So it's just a quick example of multimodal sentiment analysis. It's basically, for example, if I'm looking at an image and I see the image of a person sitting on a bench and it's a bright day, that might give me some perception that the sentiment of this situation is good. But then adding the sound in there, perhaps he's hearing some really bad news that he got laid off or something, and he's processing that's on his phone. Whatnot would give me a more complete interaction of the sentiment of the image or the sentiment of the situation. Visual question answering means what's going on within an image and asking things about it, like what is happening in this image? What is the color of the vest that the person is wearing? What is their approximate age? Things like that. So where are they located? So I'm going to try to play this video. And this is basically, again, I don't know if the sound is going to come through.
Okay, let's do some tests. Tell me when you see something that makes sound.
I see a speaker, which makes sound.
What is that part of the speaker called?
There you go. There was the sound.
That is the tweeter. It produces high-frequency sounds.
Give me a creative alliteration about these.
So by the way, who knows what this is right now? Okay, great. So this is Google I/O. This past year, they demonstrated their Project Astra, which was a multimodal assistant, which you can see what it can do for those who weren't here.
Okay, let's do some. What is that part of the speaker called?
That is the tweeter. It produces high-frequency sounds.
Give me a creative alliteration about these.
Creative crayons color cheerfully. They certainly craft colorful creations.
What does that part of the code do?
This code defines encryption and decryption functions. It seems to use AESCBC encryption to encode and decode data based on a key and an initialization vector, IV.
That's right. What neighborhood do you think I'm in?
This appears to be the King's Cross area of London. It is known for its railway station and transportation connections.
Do you remember where you saw my glasses?
Yes, I do. Your glasses were on the desk near a red apple.
You'll probably remember Google Glass, maybe. Yeah. Well, they're trying to bring it back.
What can I add here to make this system faster?
Adding a cache between the server and database could improve speed.
What does this remind you of?
Schrodinger's cat.
All right, give me a band name for this duo.
Golden Stripes.
Nice. Thanks, Gemini.
Okay, so not an advertisement for Gemini or anything, but demonstrating the capabilities of Gemini integrated into Multi-Modal Assistant on an Android device. I'm at heart an Android developer, so that's why that's something that strikes me as like coming soon, kind of to a handset near you. Awesome thing. So the first thing, is anyone familiar with the clip model here? Okay, so the clip model, I'm glad many hands didn't raise because then I get the privilege of explaining it. So CLIP stands for Contrastive Language Image Pre-Training. So it's an open source multimodal AI model that understands and connects visual concepts with text descriptions. So if you have images and you have text, both of those are essentially as part of inherent understanding of the model, baked into its latent space and its embeddings. And you can use this model to find a particular object in an image and determine, oh, what is the text associated with that image? If the cat exists in this model would pick it up. So the model was trained using a vast data set of image and text pairs, learning visual concepts from the internet. And so when I say vast, the initial training set was approximately 400 million images. And it's that by today's standards is actually not that big. Like models like these are now advanced by billions and billions of images, which is no mean feat to get good labeled image text pair data. And so CLIP can be applied to diverse applications, such as zero and few shot learning, which means that, and CLIP, by the way, came out in 2021. So it's actually an older model, technically speaking, but it's quite powerful in the number of applications it's been used in. And it can learn things from images that it hasn't seen before. So, for example, if it can pick out, if it hasn't been trained on a very specific rare cat in a very specific weird position, it can actually determine that's a cat because the concept of zero-shot learning in the way that it understands what its multimodal embedding space looks like. And so there's a lot of detail in how this works, but like just giving you an example of this in a CLIP demo workshop thing that I put together, a quick demo implementing the CLIP model.
CLIP is the OpenAI framework, open source.
You can really hear what's going on here.
Framework for doing visual object detection. That's pretty popular. It's based on the Vision Transformer. And the simple example that I have here is just taking an image of a cat. So I have this image of a cat here. And then, so basically what we do, we set up our CLIP model, and then we set up our CLIP processor. So I have this all coded up here to do this. And we pretty much run the processors in order to make sure we condition the input to be ingested by the CLIP model. And then I have image captions here, which I have listed as cat, dog, mouse, horse, boat as categories of image captioning that the CLIP model will detect as a percentage of being input represented in a specific class. So I'm going to run this real quickly. And what should happen is clip should run and give us an output that shows that we are a certain percentage of cat, dog, etc. And so the output is 96.91% cat, 1% mouse, 1% dog, 0% boat, essentially 0% boat and horse. So now let's use different captions for clip. So again, if we use the ImageNet captions, because clip has been trained against.
So just quickly, ImageNet captions are basic. ImageNet, the ImageNet challenge was a challenge that for image training and image model performance. It was a competition that essentially tested whether image models could perform to a certain level years ago. There was called the ImageNet challenge. So captions associated with ImageNet are a bunch of captions of different objects. So instead of just I initially loaded this model with 5 different captions, which is why it gave a percentage over only 5 different things. But if you load thousands and thousands of captions, it's able to segment much more specifically percentages along more specified categories of things. So you'll see the rest of this.
A ton, millions and millions of data points. So I'm going to give a wider variety of different classes. And if I run this, as you can see, clip now runs, and it now has a harder time determining what specific cat it is, but thinks it's mostly a Madagascar cat. So one thing that's really cool about clip, it has demonstrated the ability to do zero-shot learning.
So basically what that setup was, let's see. Let me just make sure I'm back. Okay, basically what that setup was, it was to demonstrate how models like clip are used as part of things like DALL-E, or like, not DALL-E, like GPT vision, other types of vision models that are able to understand information about environment. It's done through the concept of multimodal embedding spaces. And so here's an example of a system that's a very simple system.
Shafik, we cannot see what's on the left, so could you tell us?
Oh, what's on the left? Okay,
yeah.
That's being covered by that video thing? Okay, so what's on the left is a query called wild animal, right? Thank you.
Okay, thank you. Yeah, that's better.
Okay, technical difficulty. So wild animal, right? And so essentially when you input, like you can call this a cross-modal search query system, right? So input wild animal into your query. What happens is a semantic embedding is created using a straightforward, fully connected neural network, an MLP. And let's say based on that, some images come up, right? And you have now you have an image. Images are learned again using things like CNNs or vision transformers. And so you will create an image embedding. And to kind of understand and cross-correlate the two images, the image embeddings with the text embeddings, you have what's called a correlational function, which is what I'll get into a little later about how these two things are matched together. And correlational models have what's called a correlational loss function, which is you're attempting to minimize the correlational loss, meaning you're trying to maximize the correlation between these two objects in the same embedding space. And so this is the kind of magic about how images and text are understood together. And so when you're building a system like this, models like Clip are essentially doing something like either correlational loss, or you might have heard of contrasted loss, different ways of matching, different types of mathematical methods of matching things together. So moving forward, so here's an example of visual image search. Okay, let's see. I don't have too much time, but okay. So essentially, I'll just describe what's kind of happening here. The visual image search essentially does the same thing, but it's a little more advanced in the sense that now, if you combine a model like Clip with another model like a mask RNN model, or some sort of more bounding box detection model, you can do things like create like this search system is the implementation that I've put together, a simple implementation in Colab of combining clip with a text understanding pipeline. And so you can just get, if I search for cat, I put the query cat in, it'll bring up all the cat images. These images are not pre-labeled, by the way. It's actually doing the machine learning to understand these images. And if I put in dog, it should bring in images of dog. And so sometimes things get confused in a situation like this is if I have a model that's like trying to determine if something's like not sure what it is, it might detect that this cow, like it does say cow, but it also says maybe 70% person. So it's detecting a person on top of this cow. So these are not all perfect systems, but more advanced models with more advanced scale can lead to more advanced and more accurate representations. So I'm going to skip the kind of neural style transfer stuff because I wanted to, well, what I'll do is like, I'll just quickly go over this and that'll be pretty much me wrapping it up. So if people are familiar with the concept of neural style transfer here. Okay, great. So basically what that is that if you take an image, right, and I'm going to use Stable Diffusion to do this, and I want to style it in a particular artist style, I will go to like a model like Stable Diffusion and ask it to create a car in the style of Michelangelo, right? Or a car in the style of Van Gogh. And so these are unique cars that are created in a particular artist style. There's been a lot of controversy about the concept of neural style transfer because essentially artists are having their images, their styles essentially stolen, and the works that they've been applied to are resold under the artist's name, and they lose royalties. Lots of issues with the concept of style transfer. In the negative, there's lots of good things, right? In terms of like quick prototyping, but there's also a lot of issues there. So the reason I'm bringing this up, and so if I keep going through the model, you can see different cars with different styles. The point is there. You can do the same thing with videos. Like this is a video of me talking, and then moving through it, I play this waterfall image style, right? And I have this video of me being essentially applied to this style. And, zoom in. Okay. So I don't know if anyone would see. Let's see if we can see this one more time, a little bit closer. Yeah. So this is like the video again, me talking.
That video is one that.
And so just application of the style using neural style transfer, and I'm using a fast neural style transfer algorithm to do this, which is based on the VGG network, which is an older a convolutional neural network model, which can actually transfer frames. And so as you can see, that's a pretty interesting technique. But the issue again is that this is a challenge for people who don't want their styles essentially taken without their permission. So what essentially I'm working on as a part of this using Clip, because Clip can do this sort of more advanced multimodal understanding, is we can match styles and content of generated images to known artwork. Clip is one model that helps disentangle content and style elements from images, and the multimodal pipeline here, that a multimodal pipeline can help provide metrics to determine if a style is associated with an artist. So, for example, like if I demonstrate this is my artist search finder, and if I pick out images from a particular artist, it can give me a percentage associated with that artist, and it can give me it'll say like a lower percentage associated with other artists. And so this is a pretty tricky technique because this is, again, a little inexact science, the concept of how styles are actually transferred, quite complex and for another time. So again, I don't have too much time to go over everything, probably like a minute left or so. But I will say that one of the things that I want to quickly discuss is that the difference here between standard machine learning and the way that multimodal learning works is through the concept of multimodal fusion. So essentially, this is an example of there's different ways of fusing the data together. You can either fuse the data together first and then attempt machine learning on it. You can attempt machine learning on it first and then fuse the data together, or you can do some sort of hybrid. So the different techniques have different drawbacks and different advantages. For example, the concept late fusion, early fusion. Early fusion means fusing, for example, all these feature vectors together that are created from all these feature creation techniques and doing early fusion. And so that means early fusion, and then SVM is, for example, a support vector machine. The learning occurs through there. And then alternatively, again, on the late fusion side, I have all these individual learning pipelines occurring and then fusion occurring afterwards. So then you have late fusion. The early fusion versus late fusion trade-off is that if you fuse early, then you get a much more complicated combined output, right? Like if you mix images with words, with sound, with text all together as one jumbled bunch, then your machine learning model is going to have to do a lot of work and be very, very robust to be able to learn things from all of those. But there are advantages because you have tons of information that you would lose if you did late fusion, right? And learn everything individually and then tried to fuse everything together. The alternative is that late fusion can be more efficient in many ways than early fusion. In other ways, early fusion can be more efficient. It depends, again, and there's hybrid fusion strategies like fuse some data, then learn, then fuse it again down the line. And then there's other techniques to do this learning more effectively. So again, what I'll do is I'll leave this at this point. There's a lot more interesting stuff. I might actually put this for a part 2 of this talk.
Yeah, that's a good idea.
Yeah, because I do have to go quite in depth. So I do appreciate it. Thank you.
Thank you. Thanks, Shafik. We still have time for questions. So if anyone have a few questions.
Bring the first slide again, the
Yeah.
one with the QR code.
The QR code? Oh, you mean all the way in the beginning?
With the code, I think you had a slide with the code, right?
Oh, that's like my first slide. This one?
Yeah.
Okay, that's just my LinkedIn.
Yeah. Early fusion versus the late fusion slide that you had.
Mm-hmm.
So what kind of a mathematical quantity can I compute which would tell me like what stage I should use? Like, is there something sharp that I can see?
Okay, so that's interesting, and that would have actually gone into the later. Thank you for that question. So that would have gone into the later slides that I have about like the specific models that actually do the fusion, which are one category is called deep correlational autoencoders. So essentially, it's actually it's challenging because the mathematical quantity that you run across the curse of dimensionality whenever you do fusion at all, because you expand your dimensions by a multiplicative amount. So essentially what people do is there's several ways of doing this, and there's research on how to do this more effectively. But what some people will do will run this against like different fusion models. For example, this deep correlational autoencoder model, and start looking at the inability to scale of this process. For example, the slowdown of the model being able to fuse data effectively, and the rate at which the data is scaling. And that metric will kind of inform you that essentially there would be a performance disadvantage to further not to fusing the two particular inputs as effectively at this point, as opposed to, and then the thing is, what's interesting is because there's another factor here in the way that I'm talking about loss functions like correlational loss. Correlational loss is a very straightforward, simplistic loss function that's based on Pearson correlation. So when you're looking at like loss function metrics in order to determine whether your fusion model is performant or not, you're actually not. You need to actually do some more advanced type of loss function learning. So you would do something like multimodal loss function. You do like a multimodal matching function. You could actually create a multimodal matching function, and that matching function is learned through its own models, its own neural network models. Then if you can find an optimal function to do that cross-modal fusion, then you can actually, then that might be a good metric to move forward with to determine whether this I should fuse now or later, because the cross-modal matching function can vary wildly based on what point in the data that you're trying to fuse. For example, if you have a very rich image data or very rich video image data, and you're trying to fuse that with like a very rich sound data, that could vary throughout the course of the sequence of inputs of each of the frames. It may, in that case, there may be times when certain sequences are actually better to do the fusion first on versus other sequences. You get what I mean? So it's actually not like, there's not like one metric that says that, so you're going to have to actually do machine learning to determine the best metric to find at what point should you do. And this is actually a much broader topic, honestly, where you could talk about hybrid fusion. And I'm going to move to a different question, but essentially the scale of this rises because you have different types of combinatorial interactions, going all the way from simple additive to high order polynomial tensor fusion. So in each of those cases, it becomes much more complicated. Sorry, that was too long an answer.
Follow-up question, but I'll ask you later.
Okay, great.
Any more questions?
Yes.
A very simple question. So the most successful multimodal models that most people are familiar with are the recent ones from OpenAI or Gemini or Anthropic called 3.5. Do you know how they did the fusion? Have they discussed this?
They're not totally open about their techniques that they're using under the hood. They're, for competitive advantage purposes, they're not actually really talking about those ideas. The complete context of my presentation would have gone into general methods of fusion that they would probably be using. For example, it's a common fusion technique is, again, I mentioned the deep correlational autoencoder. There's also what's called a multimodal neural network. There's some variant of these techniques that are being used, along with some more well-known ones. For example, Gemini is under the hood using things like vision transformers, SWINT transformers, other more advanced versions of the transformer architecture to do some of this. The general techniques are known, right? And papers are released on them, but the specifics, they're not going to release the secret sauce in my understanding, or they might have, but that's my perception at this point. I haven't seen. Yeah.
That's still helpful. Thank you.
Okay, no problem.
Any more questions? All right, that was awesome. Thank you. Now we're going to take a short break, and as Shafik mentioned, visual transformers, that actually happen to be our next topic. And we're going to get back in 5 minutes with Aninja Dave, and he'll tell us about visual transformers. Thank you.